Hi everyone. This was one of the only lessons that I did not have a recording for from last semester. Don't know why, but I just didn't. So you're just going to hear me today. Hope this lesson goes well. So today we're starting chapter 15. Chapter 15 is my favorite chapter. It's on multiple integrals. In all honesty, I have no idea how this image here relates to multiple integrals, but I'm excited to find out. So anyway, today we're just doing a simple lesson. Hope that it goes well. Let's get started. So today we're doing 15.1. It's called double integrals over rectangles. We're really going to focus more on actual double integrals tomorrow, and today we're going to learn how to approximate them using rectangular prisms. So today is more of a day, kind of a lead-in to double integrals. This is 15.1a. Let's turn on the stylus, 15.1a. And then tomorrow we'll learn how to actually evaluate double integrals. Okay, so before we get started on how to approximate double integrals, this is just a screen that shows is supposed to refresh your memory on how we approximated single integrals last year. So if you remember last year, we learned something called Riemann sums, and it's a way of using rectangles to approximate the area under a curve. We did this using left rectangles, right rectangles, midpoint rectangles. Here we have a variety of different rectangles where the rectangles are all being kept at the same width. And then the height is just determined at these random points within each interval. Today, we're not going to use random points. We're going to have specific points to use, just like we did last year when we would say use all righties or all lefties. So anyway, just remember that last year we learned that to approximate, so a single integral gives you area under a curve, and to approximate it, we would break it up into rectangles and just add the area of each rectangle together. So today what we're going to do is we're going to use double integrals, but to find the area under a surface. So now we have this surface, if you can see the surface right here, and this surface, the projection of this surface onto the XY plane forms this rectangle R. And what we're going to do is find the volume of all the space between the surface and the XY plane bounded by this rectangle R. So all this space that's in here is what we are going to be approximating, the volume of that space, and we're going to approximate it using rectangular prisms. So the first thing we're going to do is we're going to divide R into a bunch of little rectangles like this, and then we're going to extend these rectangles up onto our surface, pick a point to find a height, and then find the volume of this rectangular prism, which is really just the area of this base times the height. So this image here is showing you how to break R up. They're picking some sample point, and I kept this terminology in even though I don't use this, but they're picking a sample point x sub ij, y sub ij, and we'll talk more about what I and j represent, but they're more used in our summation notation that we're going to be talking about. So anyway, but we pick a rectangle, like some rectangle right here, we pick some point within that rectangle, we find the height of the surface at that point, and then we find the volume of this prism using the area of this rectangle times the height at some chosen point inside of the rectangle. And then we do this for all the rectangles, add them all together, and what we end up with is something that looks like that. So what we're doing is we're approximating volume under a surface between the surface and the XY plane using these rectangular prisms and adding them all together. So this notation right here that you're looking at, this, if you remember sigma notation, so we're letting, as I goes from 1 to m and as j goes from 1 to n, we're taking the function value, which is your z value, times the change in area, which is the area for that particular rectangle. So your M value right here, that's how many rectangles we're splitting the region up in the X direction. So whatever we go from, there's M rectangles in here, and then in the Y direction, there's N rectangles this way. And so we have this M, I'll do it over here, M by N shape. We have M by N rectangles. And so we take the sum counter goes from 1 to n for all of our rectangles in the y direction. Sum counter goes from 1 to m for all of our rectangles in the x direction. Take all of those rectangles, take their area times the height at some chosen value inside of each rectangle, add them together, and we get the volume of this shape. So now we're going to take, if you kind of have been following a little bit, we haven't done the examples yet. That's okay. We're going to kind of move forward and then back up a little bit. So if we were to take the limit as m and n both approach infinity, what we're talking about is fitting infinitely many rectangles inside of that space. So if we take the limit as both m and n approach infinity, your volume goes from an approximation to an exact volume. So now what we get is an actual volume if we go take our number of rectangles to infinity. So what is another notation for this? Well, in the past, if you remember, if we took the limit as the number of rectangles approached infinity, and then of the sum of all of those rectangles, and that was just in a single direction, we would get a single integral. So I'm just going to refresh. Let's just remember. So in the past, it's been a long time, but in the past, we did the limit when we found the exact area using rectangles, did the limit as n approaches infinity of the sum as I goes from 1 to n of f of x sub I, so whatever the height was at that point, times dx, which is the width of the rectangle, right? Now all we're doing is adding another dimension to this. So instead of dx, a single variable, we have this delta a, which we could write as dy dx with both a width in the y direction and a width in the x direction. You take these two widths, put them together, and you call them dA or delta A, which is really kind of this times this. So you really get that change in area. Okay, so then we have our height. Remember that our z value has two inputs now, so we need an input for the x and an input for the y. And then we have two sums, sum in all the x directions, sum in the y direction, and therefore we get this double integral. So this double integral represents this limit with this double sum that actually gives us the volume under a surface that has been bounded by certain x and y values. Now, what we've done here, if you look, it's generalized. It's just called this R. R is just the name of the region. If you remember, that was the region in the XY plane. You had that surface. Okay, so we had that surface and we had that region R. Okay, so our R, which represents that region down here, later on when we actually evaluate these integrals, we'll put in specifics. We'll put in x's and y's with limits from x goes from something to something and y goes from something to something. So there will be, in the future, there'll be numbers here and here and here and here, and you'll have dy's and dx's over here. But right now, this is just kind of a general formula. So they've got an R to indicate the region that we are integrating over, and this delta A to indicate that we are doing a dy dx, kind of a two-dimensional area that we are integrating over. All right, so, this is just telling you that the sample point can be chosen at any point in the subrectangle, but if you always pick the upper right-hand corner, it makes your formula become easier. So it takes that funky little asterisk thing they had going on, and turns it into a much simpler formula. This is kind of like when we did our exact area last year. The exact area formula we used was always for right-handed rectangles. Very similar concept here, just in 2 dimensions. It's still an exact volume. It's just it makes the formula simpler if you're always using the upper right-hand corner. That's all that this is saying. Again, you don't have to have this memorized. We just have to learn how to do it. Which brings us, wait, I thought we were coming to our first example, but one more last little thing. This is just reminding you then that in the most simplest version, if we want the volume of the solid that lies above some rectangle in the xy plane and below some surface, z, which is some function of x and y, then that volume is the double integral evaluated over the region R. Now, this is volume. Remember, it's a lot like area. So last year, remember, if we had some function that went below the x-axis and above the x-axis, and we did the integral from here to here, we did not get the area. Same thing holds with volume. So what happens with volume in the xy plane is if the region's down here for part and up here for part, you're going to get negative answers down here and positive answers up here. So the only way to truly get volume is if everything's above the x-axis, if you do like an absolute value, or multiply, find where it's below and just multiply by -1 or something like that. But just know that volume, you only get volume, like true volume, if your function is above the xy plane. Oh, and the last thing, this, just so you know, this thing that we've been talking about is called a double Riemann sum. That's all I'm taking from the screen, is that it's called a double Riemann sum. And, and this is just talking about how the function has to be positive. There you go. And we're finally at the first example. Yay! Okay, so here's our first example. Estimate the volume of the solid that lies above the square from 0 to 2 by 0 to 2. And this is like your x and this is like your y. So your x's go from 0 to 2, your y's go from 0 to 2. And then we are below this elliptic paraboloid, right? So up, like somewhere up above this xy plane in space is some paraboloid floating above. And we're going to find the volume between that and this xy plane. Divide R into 4 squares and choose the sample point to be the upper right-hand corner of each square. Now, sometimes they tell you how many squares to divide, and sometimes they give you the m and the n. For example, in your homework, you might see a problem where it says m equals 2, n equals 2. This is how many, like your m means how many rectangles in the x direction, and your n means how many rectangles in the y direction. So just know that you might see it with m and n, or you might see them just tell you how many to split it up into. All right, so how do we find our volume? So our volume is approximately, so the nice thing about this, each rectangle has the exact same area. You could do, I don't know if you remember on Riemann sums, we used to do width times height plus width times height plus width times height. But if all the widths were the same, we could kind of factor them out and put them in front. Same thing here. We're going to do area times height plus area times height plus area times height. But since all the areas are the same, we can factor the area out front. And then all we're really doing is adding the 4 heights together. So how are we finding our heights? We're plugging these 4 points into our z function. So if I did z of 1, 1, I get 16 minus 1 minus 2, which is 13. Z of 2, 1, I get 16 minus 4 minus 2, which is 10. Oh, please ignore the dog. Okay, if I do z of 1, 2, excuse me for a moment. If I do z of 1, 2, so I get 16 minus 1 minus, let's see, 2 squared, 4 times 2 is 8. So I end up with 7. And then my last one, I'm going to put up here, z of 2, 2. I get 16 minus 4 minus 8, which is 4. So my 4 heights would be 13 plus 10 plus 7 plus 4. And so my approximate volume would be 23, 30, 34. We don't have any units. That's okay. We're just going with whatever numerical answer we get. All right, the last problem, the second example that we're going to do is using what they call the midpoint rule, which is what all books call it, but I just say think of it as using midpoints. Again, this time they're presenting it with m equals n equals 2, which just tells you we're doing 2 rectangles this way and 2 rectangles this way. Okay, so m tells you how many in the x direction, n tells you how many in the y direction. Okay, so we're going to approximate the value of this integral where r is the region bounded by x's from 0 to 2 and y's from 1 to 2, which we've drawn out here. So our x's go from 0 to 2, 0 to 2, and our y's just go from 1 to 2, which means that our widths of each rectangle is going to be 1, but our heights are just going to be a half. All right, so what we need a z function. What's our z function? Our z function is the x minus 3y squared. That's our z function that we're plugging into. And what are we going to plug in? We're actually going to plug in the midpoints of each region. So let's go ahead and find our ordered pairs first. So our the first height that we need to find would be this midpoint right here. This midpoint would be at 1/2 for our x value, and then it's the average of these two guys right here, 1 and 3/2. So halfway between 2/2 and 3/2. So between 4/4 and 6/4 is 5/4. Okay. All right. So this point is 1/2, 1/2, 5/4. And then our next point right here would be 3/2. And then the same height, 5/4. Our next point up here, so it would be 1/2 and then plus another half, so 7/4. And then our last point would be 3/2, 7/4. Okay, so and then let's figure out our areas too. So our area of each rectangle, they're all just 1 by 1/2, so we have an area of 1/2 that's going to go out front. I am going to pause, use my calculator to find all of these because I don't feel like doing all this by hand. It's like a miracle. Look at that. We've got our 4 y values. But I want you to notice something. All 4 of these y values are negative. I had written that this was an approximation of the volume. It's not because our answer is going to be negative. So I'm going to rewrite that and just say that our integral over region R of our z function dA is approximately 1/2. That's our area. I'm going to write that's our area of our rectangle times our 4 heights, -67/16 plus -51/16 plus -139/16 plus -123/16. And then if we put all of that together in our calculator, sorry, I'm going to make you wait for this one because I didn't put it in, plus that, plus that, plus that. I end up with a final answer of -95/8. And that would be my approximation for whatever the value is of this integral. Now, obviously, you know that integrals have more meaning than just area and volume, but in this unit, we are going to focus primarily on integrals that give us volume. We are going to spend a little bit of time on a couple other applications, but most of what we're going to do in this unit is going to be using these double and triple integrals to find area and volume. So today we are just approximating. Tomorrow we're going to actually evaluate the integrals and find the exact volume. Hope you all have a great